Good morning. So I'd like to give this tutorial in English, of course. So the title of this tutorial is on speech synthesizing reason techniques, including two parts. So one is on the end-to-end technology based on the Tacotron. Another part is on neural waveform modeling. So we will give, me and my colleague will give this talk into two parts. So I will give the first part on the neural waveform modeling. So originally the title of this talk would be WaveNet tutorial, but when we were preparing slides, we realized there have been so many new waveform models that have been proposed in the last few months. So we changed the title slightly. So this tutorial will be about some new neural waveform models. So we will give a brief overview of different categories, different groups of this kind of neural waveform models. So I hope you could enjoy it. Before I start, just a short introduction. So I'm Shin, now a postdoc and NII, Yamaguchi lab. I got my PhD last year from the same lab. So both my PhD and my master's degree, I was working on the speech synthesis. You could find the some of the work on the GitHub. Okay, let's begin. So since the title of this tutorial is on text-to-speech, so first I'd like to briefly introduce the idea of the text-to-speech synthesis. If you are not familiar with it. After that, I will give the tutorial on the neural waveform models, and finally a short summary. So when we are talking about TTS, actually we mainly are talking about this kind of technology that converts the text into the speech waveforms. You may see many kinds of applications of TTS. For example, the cell phone, the Siri, and also the talking robot. And our lab at NII has been working on speech synthesis for a few years. So here I'd like to show some samples from our NII's TTS systems. So on the left side will be one natural sentence read by the human speaker. And on the left side, on the right side will be three samples from three TTS systems on NII. So one 6 years ago, 3 years ago, and last year. So first, the natural sample.
驚いて振り返ると、目の前に薄汚れたワイシャツにヨレヨレのズボンを履いた青年が立っていた。驚いて振り返ると、目の前に薄汚れたワイシャツにヨレヨレのズボンを履いた青年が立っていた。驚いて振り返ると、目の前に薄汚れたワイシャツにヨレヨレのズボンを履いた青年が立っていた。驚いて振り返ると、目の前に薄汚れたワイシャツにヨレヨレのズボンを履いた青年が立っていた。
So you could perceive the change of the quality there, especially the last one. Sounds quite close in terms of quality to the natural speech. So actually this system used one of the neural waveform models that I will introduce today. But I'd like to mention that neural waveform model is by no means the only factor that influences the quality of a TTS system. So there are so many components in the TTS system. So let's see this kind of architectures. So one classic so-called pipeline architecture of TTS system looks like this. So given the text, we need a text analyzer to derive some linguistic features. So for example, in Japanese case, we need to know the pronunciation of each word and also the pitch accent of each word. The famous example is pitch accent hashi, hashi. You need to know it. Given these types of linguistic features, we use acoustic models to convert the linguistic feature into acoustic features. For example, spectrum features, fundamental frequency, or band periodicity. And finally, given all these kind of acoustic features, we use a waveform model to convert it into the waveform. So this is where we use the waveform model in a TTS system. And of course, this kind of pipeline architecture is not the only one type of architecture we can use for TTS. For example, with neural networks, we can merge the acoustic models with waveform model together, so that we can directly convert the linguistic features into the waveform. So that's one way to do the TTS. But one more ambitious one is like this. We just use one single piece of model to convert the text directly into the waveform. So that's what is called the end-to-end TDS. As you can see, there are so many components we need to consider, especially for the first two types of TDS architectures. So, well, it's impractical to explain all the components in a single tutorial. So in this talk, in the first part of this tutorial, I will only talk about the waveform models. Even for the end-to-end TDS, actually we need a waveform generation modular at the end of the system so that we can generate the waveform. And for the second part of the tutorial, my colleague will give the talk on the end-to-end TDS. Okay, that will be the content of this tutorial. Okay, let's move to the neural waveform modeling. So first, let's give the definition of a task. So suppose we are using a TDS system where the system has predicted spectrogram from the text. So what we need to do using a neural waveform model is to convert the spectrogram into the waveform. Well, if you are familiar with the signal processing techniques, you may know that we can use inverse STFT plus some additional techniques to convert the spectrogram into the waveform. But that's not what we are going to do using neural waveform models. So what we're going to do is like this. Suppose the spectrogram is represented as a matrix, so two-dimensional matrix. We have n frames of vectors. Our goal is to generate a waveform sample, or a sequence of waveform samples, where the length is t. So this is the definition, the task we want to do. So more specifically, if we want to build the neural waveform models, it looks like this. So we want to find a probabilistic model so that we can compute the distribution of the waveform sequences giving the input spectrogram. So in this case, it can be written in this formula. But how can we do that? It seems to be quite difficult, right? But actually, we could think of some simple ideas to convert input into the output. That would be like this. So the first question we need to solve is this one. So the input sequence is not, the length of the input and output sequences are different. So what we want to do? Well, the idea is quite simple. We just duplicate each of this vector in one frame multiple times so that the input sequences would be equal in length to the output sequences. So as long as the input and output have the same length, then we can use simple neural networks to convert input sequences into the output sequences. For example, using the feed-forward network. And then we can compute the distribution at the output layer, and then we can evaluate the likelihood of the waveform values, or we can generate samples from the distribution. So, of course, we could do something more complex. For example, we just replace the network, a feed-forward one with a recurrent one. We can do it. Right? Of course, we can also use so-called dilated CNN like this. So the same way, just compute the hidden features from the inputs and give the output distributions. That's all. In fact, no matter what kind of network we use, when we use this kind of naive approach and train the network, actually we assume the distribution of the whole waveform conditioned on the spectrogram can be written in this way. It will be a product of the distribution of the waveform value at each sampling point. So, would this kind of approach work? Here is one sample from this kind of naive model. So it sounds muffled. Yeah, actually, you cannot understand the word it says in this generated speech. So what's the reason for that? Well, one simple reason is that the waveform is get over-smoothed in the time domain, so you cannot hear anything. What's the reason for the over-smoothing effect on the generated waveform? It's this. So we know that waveform is highly correlated sequences. So waveform sampling points, for example here, would be highly correlated with each other. But the model we assume looks like this. they assume that the distribution of the two waveform sampling points are independent from each other. So you could see the mismatch between the data we want to model and the model assumption actually we use. So this is a problem with the naive approach. So what we can do with it? As you can imagine, the first method is just to replace the naive model with a better model so that we can take the dependency of the waveform into consideration. Another approach is, instead of training the network by measuring the MSE or cross entropy at each time point, we could change the training criterion. The third approach is like this. Suppose we could find the transformation so that we can transform the waveform sequences into a simple, easier signal, so that we even use a simple model, we can model this output signal from this transformation. That's the third approach. Of course, the fourth approach is just a combination of the first three approaches like these. So actually, these four approaches have been used by the recent neural waveform models. So if I draw a picture like this, we could divide the recent neural waveform models into four groups. So for the group using better model, basically they use autoregressive models. So that's the WaveNet and sample RN, and also some variants of the WaveNet, WaveRN, FFT-net. For the transformation-based approach, it will be the parallel WaveNet, Clarinet, and also the new model called WaveGlow. And for the third approach, actually that's the two models proposed by us, by our group. And fourth group, you can see the LPCNet, LP WaveNet. Basically, they borrow the idea of signal processing, a linear prediction model, there combined with the WaveNet. That's all. So this will be the four groups of neural waveform models, recent models. You could find reference papers in the appendix of this slide. It's impractical to explain all the models in this tutorial. So I'd like to just maybe explain one of the models from each group. So first one is autoregressive models. So this is a naive model that I have shown before. Notice that the distribution of the waveform can be written as product distribution. So what autoregressive model does is actually it's quite simple. It just feeds the waveform value of the previous sample step into the next as the input to the next step. So as the red curve shows, you can see that. So mathematically, you could show that once we feed the output waveform values into the input side, we assume the model distribution like this. You can notice here, at each time step, the waveform value would depend on previous samples. That's how the autoregressive models introduce or models the time dependency of the waveform. Of course, in order to ensure that the waveform models, the autoregressive models can learn the dependency, we need to use a specific training technique. That's called teacher forcing. The idea is actually quite simple. So suppose this is the training stage of the model. So we have natural waveform from the training data. We have input. So what we need to do is just to propagate, just feedback the natural waveform into the input, and then we just propagate the hidden features layer by layer until we get distribution at output side. So this is easy for the training stage. However, in the generation stage, as you can imagine, we have to generate waveform samples one by one. So for example, we need to generate first example, feedback, generate a second sample, feedback. And we need to repeat the process for the whole sequences. So you can imagine that the time we need to generate a sample, generate the waveform sequences would depend on the length of the waveform. So it's quite time consuming. That's a problem with the autoregressive models. Okay, so I have introduced the basic idea of autoregressive models. So let's see what is actually done for example, in the WaveNet. In fact, so here's a picture you may see from the paper. Actually, the architecture of the WaveNet is quite similar to what I am showing in the previous slide. But the WaveNet, of course, add additional hidden layers between each layers of this dilated CNN. For example, it added this kind of gated activation function, also the skip connection there, and it will feed the conditional features into each one of the hidden layers here. So there are so many details about how we compute the hidden features in WaveNet. You can find the slides on my website. So that's basically the idea of the WaveNet. It's quite, well, actually it's quite simple. And a related model to the WaveNet is actually sample RN. It's also based on the autoregressive assumption. It just differs in the way in that how do we calculate the feedback data. But anyway, so that's the basic idea of an autoregressive model. As you can see, as we have mentioned before, one general issue with this kind of autoregressive model is it's very, very slow to generate a waveform sample. So what we can do if we want to improve or accelerate the generation speed. So basically there are two types of approaches in the autoregressive groups. So one is just to simplify the computation. Another one is just to borrow some knowledge so that we can accelerate the generation speed. So for the first group, we have WaveRN and FFT-net and the related model. And for that one, for example, we have sideband WaveNet, which divides the signal into sideband, so that we can downsampling the waveform in each sideband. We can generate, so that we can accelerate the generation speed in each sideband. But that's basically the two groups of model, or we can try to build in order to improve the generation speed. So here, I'd like to briefly introduce the idea of the WaveRN there, because I think it's quite important for waveform modeling. So let's recap the idea again. So why waveform, the WaveNet is slow in generation? Because waveform assume this kind of linear time autoregressive dependency. As you can see, suppose we have a sequence of samples. So the sample would depend on the previous samples. And we need to generate the samples from left to right. For this case, we need 16 steps to generate whole sequences. So the idea of the WaveRN is this one, subscale AR dependency, also a batch sampling. What it does is, again, it's quite simple. So instead of form the sequences as just one-dimensional sequences, we could form the sequence of samples as two-dimensional sequences. Based on this figure, we could build dependency like these. So it's more flexible than linear case. More importantly, when we generate samples from this kind of matrix in the generation stage, we could generate multiple samples at the same time. So here is one example. First, we generate first example, second one, and you can see at the third step, we generate this sample and this sample together. So when we generate this sample, we will use the data that we have generated from 1 and 5. So this is how it generates in the generation phase. It will look like this. So if we count the number of steps we need to generate the sequences, it's just only 10 steps. Well, of course, so this is a simple example. Actually, in the paper of the WaveRN, well, it's used, say, you can generate multiple samples. In this case, it's 3 samples together. Of course, 4, as long as the sequences of the waveform is longer, we can generate multiple samples together. So that's how it accelerates the generation speed. So that's one story about the WaveRN. But let's remind you that the one idea here is to formulate the waveform as a matrix so that we can build the dependency in the matrix instead of in the one-dimensional waveform sequences. So here is the actually, even though the WaveRN compared to the WaveNet is faster, but it's still quite slow because the generation speed still depends on the length of the waveform. It still needs autoregressive assumptions. We need to generate the samples one by one or row by row. So what we can do if we want to further accelerate the generation speed without using the autoregressive models. So that's the approach of the normalizing flow. So for the normalizing flow-based approach, the idea, as I mentioned before, is like this. So although the waveform is highly correlated signal, but suppose we can find the transformation f there, so that we can transform the original waveform into a new signal d there. And if this d has a weak temporal correlation, so that this d can be modeled by using a simple model. So that's the idea. Of course, in the generation stage, we just generate some samples from the simple model and then do the reverse transformation, so that we can recover the original waveform there. And of course, the paper about normalizing flow showed this kind of horrible equations, but actually the principle is quite easy. If you read the textbook, you can find it in the class of statistics or probability theory. It's based on the principle of changing random variable. That's all. Of course, in practice, we may use multiple stages of this kind of transformation. So in most of this normalizing flow-based paper, they use multiple stages. They hope that by using this kind of multiple stages of transformation, we can convert the original target signal into random noise. So that we can directly evaluate the Z signal using a Gaussian distribution. That's the idea. So that's why it's called normalizing. We normalize the output signal into noise sequences. It's called flow because we are using multiple stages of a transformation. So that's the idea, basic idea of the normalizing flow-based approach. Of course, we could add some additional conditional features so that we can apply this kind of model for TDX. So based on this principle, we have four models: the parallel WaveNet, clarinet, and also the wave globe. So the difference between this four models is how they define this transformation function. So as I mentioned before, the parallel WaveNet and the clarinet define this transformation function in the linear time domain. But for the wave globe, it's a subscale time domain, in the same way as the wave arm there. Because the different definition of this transformation function, well, these two groups of model, they use different training strategies, as you can see later. So let's briefly explain the idea of the clarinet and parallel WaveNet. So suppose we're using this model to generate the waveform samples. For example, suppose we have generated some random noise from the Gaussian distribution. So what do we need to do in the first stage of this transformation? We just propagate through the dilated CNN, and we get the mu signal and the sigma signal there. And based on this mu sigma, we could do an affine transformation or linear transformation if we want. Just, simple transformation, and then we get the output like this. So as you can see from this figure, in the generation stage, there is no autoregressive assumption there. We can generate samples of a whole sequences of samples at the same time. So it's quite fast in the generation state. So we just repeat the process in each block, and finally we could get the waveform from the output of the last transformation block. However, that's a generation stage, right? So what do we need to do in the training stage? Remember, we need to transform the waveform into the random noise. So suppose we're in the the last transformation group here. So we're giving the input signal here, and we want to do the reverse transformation, which can be written in this equation. So what we need to do is look like this. We need to generate samples one by one and calculate the mu and sigma. So as you can see in the training time, we need to get the reverse signal step by step. It means the training time would be very slow. It depends on the length of the waveform. To briefly summarize it, as we can see, the normalizing flow-based approach is slow in the training, but it's fast in generation. For the original WaveNet, it's fast in training stage. It does not depend on the length of the waveform. But in the generation stage, we need to generate samples one by one. So what we should do? Well, the idea is just combine these two, right? That is the core idea of the clarinet and the parallel WaveNet. So in the training stage, we use the generation phase of this normalizing-based model. And we also need another so-called teacher model. So that teacher model would be a pre-trained WaveNet. So in the training stage, we generate samples from the student model. We feed back to the WaveNet. So as long as the WaveNet gets the feedback data, we could calculate the output distribution. That would be the teacher distribution. And based on the principle of normalizing flow, we could also calculate distribution for the student model. So we could get two distributions. So the training strategy of the clarinet and parallel WaveNet is just to make sure that the student could imitate the distribution of the teacher model. So that's what knowledge distilling. So that's how it works for the clarinet and WaveNet. So these two models are different from each other only in the way how they define the distribution. That's all. So that's the basic idea of the normalizing clarinet and WaveNet. But of course, you can see, although the model is fast generation, but it needs a pre-trained WaveNet in the training stage, which is not so convenient. So what we can do if we don't want to use a teacher-student model, that's the second group of the model. For example, the WaveGlow. So let's recap it again. Why the normalizing-based approach is slow in the training stage? So remember, the parallel WaveNet and clarinet defines the dependency in the linear time domain. It looks like this: generation stage, training stage. So the idea of the WaveGlow is quite simple. So if we want to reduce a complexity, the time latency there, what we can do is just to reduce the factor t there. In other words, we formulate the sequences of the waveform as sequence of vectors, and then we build the dependency among vectors. So in the generation stage, it looks like this, and in the training stage, it looks like this. Although we need to do the reverse transformation step by step, but in this case, since it's a sequence of vectors, we compress waveforms so that the training time would be greatly reduced compared with this case. So as you can see, just 4 steps, and in this case, 16 steps. So that's the basic idea of the WaveGlow there. And if you read the paper, you could find this picture there. So there is one, it seems to be simple modular called the squeezed vector. That's the magic there. Turn the sequence of waveforms into the sequence of vectors and reduce time complexity in the training stage. So that's the basic idea of WaveGlow. We have seen how borrows the idea of normalizing-based approach, and will also use a subscale dependency to accelerate the training and generation speed. But we are still wondering what we can do if we want to build a simple model, even without using the normalizing flow. So that's the neural waveform source filter model that we proposed. So this model belongs to the third group. So the architecture is exactly the same as a naive model. Very simple. The difference is here how we learn, how we define the training criteria. So the training criterion here is like this. So after we generate samples, we calculate the STFT, and then we evaluate the MSE in the frequency domain. That's the idea. Very simple. And of course, we need to do some additional work in order to improve the quality. So suppose we have the F0 as the conditional feature. Then we generate some multiple sine waveforms and also harmonic waveforms, and we merge them together. And then we just feed it as additional input to the network. So that's a network. That's all. Very simple. So let's see some examples about this network. So here is the example. Of course, we use multiple stages of this dilate CN, and you see here's the sine waveform. So if we plot, in the generation stage, we plot the spectrogram of the sine waveform, the merged one. You can see it there. The spectrogram there. You could see the harmonic there, but there is no format. As long as we go further, you can see as we are closer to the loss stage, we can see the spectrogram is more clear. It acquires the format which can be generated by the network. And here is one sample.
Much, replied Jean, as tersely.
So that's what we can do with this simple network. And it turns out this network works quite well. It's faster than the original WaveNet, at least 100 times faster. Of course, if the GPU card is large enough, that could be 1,000 times faster. And the speech quality is similar to the WaveNet, as you can see here, the last model, in both copy synthesis and TTS sense. You can find the samples on the web page, so I don't have time to play the samples here. Okay. So let's briefly summarize the models I have introduced. So compared with the naive model, we have first group use ultra-regressive assumptions, WaveNet, sample RN, but this kind of models are slow in the generation stage, so that we have parallel WaveNet and also WaveGlow. Of course, we could do a simpler model, that is neural source field model, where we change the training criteria so that we can still model the dependency of the waveform there. Of course, the title of this talk is about toolkit, our toolkit. Yeah, actually, we developed the toolkit, neural network-based toolkit, which can support the WaveNet and also the neural source field models. Of course, with some additional modification, small modification, we can use it to train the network over there. For the toolkits, you could find it on the GitHub. We prepared the scripts so that you can train the network quite easily. Just put the data there, change the configuration file, and run the script. That's all. But of course, I'd like to mention that this network this toolkit is not based on Python, I'm afraid. So, in order to, it's based on C++ and CUDA. So I also prepared additional slide to explain the principle of this toolkit. So if you want to check it, please have a try. So here's the list of reference paper there, and yeah, that's the end of the part one. I think that I will take the questions after the second part. So yeah, let's move to the second part.